Hi, in this video we are going to talk about zero order reaction. A reaction, let's say A gives products, is considered zero order when the rate of the reaction is independent of the concentration of A. That means the rate equation becomes minus RA equals to minus dCA dt equals to k into Ca to the power 0, which is essentially k. So there is no concentration term on your right hand side, therefore the rate of reaction is independent of the concentration of raw material. Now if you integrate this, then you can see that on separation and integration you finally obtain Ca0 minus Ca, which is again equivalent to Ca0 into Xa equals to Kt. Okay. One thing you can observe is that Ca0 will never be negative. Sorry, mistake. Ca will never be negative. It's wrong to write Ca0. Ca will never be negative. Okay. But Ca can reach 0. So if Ca ever becomes 0, it simply means that Xa should be equal to 1, right? Therefore, we can say that the time for which Ca0 Ca goes to 0 is given as Ca0 by K. Simply substitute this T value such that Xa equals to 1. Then you will get that the time in which the value is Ca0 by K, at that point the concentration of A goes to 0. That is, all of the raw material has been exhausted for the reaction. So this equation is valid for times which are less than Ca0 by K. For a time which is equivalent to or greater than Ca0 by K, Ca goes to 0 and we have 100% conversion. This also means that conversion is proportional to time. This is another observation that you should know, that conversion of the raw material is proportional to time. If we make a plot now of T being on the x axis and Ca being on the y axis, and if you get the slope, then the value of slope is minus k, and the x intercept when your Ca becomes 0 is given as Ca0 by K. This is the test for a zero order reaction. Now there are some interesting points that you must note for zero order reactions. So it is seen that as a rule reactions are of zero order only in certain concentration ranges, and these are usually high concentration ranges. So let me write this: reactions are zero order in higher concentration ranges. Why do we say that? We have already told that zero order means the rate of reaction is independent of the concentration term. So when can the rate be independent of the concentration term? When there is so much concentration that we do not have to worry about the depletion, right? So generally reactions are found to be of zero order at higher concentration ranges. But when the concentration decreases, if the concentration starts to decrease to that extent, then it is seen that the reaction becomes concentration dependent. So if you are able to lower the concentration to such an extent, then the reaction can become concentration dependent, and consequently the order of the reaction rises from zero. Okay, this is another observation that we need to note. So generally if you ever come across the experimental data for zero order reactions, let me draw a plot. So on the x axis we have time, and on the y axis we have xa. Okay, so let's say you have data points. Now what happens if you make a best fit curve out of this? This is like roughly by my IA estimation, it's not exactly a straight line, but let's say this is your best fit plot of the experimental data. Then till the point that the concentration is not lowered enough, you will observe that there is zero order reaction observation, and the slope of this curve, we already know ca0 xa equals to kt for our zero order rate equation. So you can simply say xa equals to k by ca0 t. Therefore the slope becomes k by ca0. But note that as the concentration decreases and with increase in our conversion value, we assume that the concentration is being consumed, the concentration of A is being consumed. So the reaction order has now started shifting. Let me mark it with a different color so that it is easier to understand. So at this point the order is changing, so there is deviation from the zero order kinetics over here. Let me write this: deviation from zero order kinetics. Okay, so this is one interesting thing. And when there is deviation from zero order kinetics, so the order is actually rising from the value of 0. Now in practical applications, where do you see this kind of reactions, these zero order reactions? Generally some cases where you can see this zero order reactions are, say, in photochemical reactions. Now the key component for a photochemical reaction is the radiation. So the rate of the reaction is very much dependent on the radiation inside the chamber where you are carrying out your photochemical reaction. Another example is a solid catalyzed gas reaction. Okay, so here the main component is the surface of solid available for reaction. Okay, so these are two main categories, especially the photochemical reaction is a very well known case of zero order reaction example. And it is important in these cases to define the rate of zero order reactions such that this other factor, like in case of photochemical reaction radiation, and in case of gas reactions catalyzed by solid, the main component is surface of solid. So we have to write the rate expression such that these factors, this radiation and surface of solid, are accounted for. So here how much radiation is affecting, how much of the mass transfer through the solid surface is affecting, those things come into play. So these are the main observations that we get about zero order reactions or zero order kinetics. That is it. Thank you.